All right, our next speaker is Libin, who's currently postdoc with us, who's going to speak about, talk about iteratively reweighted kernel machines, efficiently learning sparse functions.
Hello everyone. Today I'm gonna share our recent work, iteratively reweighted kernel machines, efficiently learn sparse functions. And this is a joint work with Damick from UPenn, Diva and Mariam from UW. Okay, so we all know that neural networks are very powerful, and people usually attribute their powerfulness to their two key abilities: feature learning and hierarchical learning. And let me take this example. This is a facial recognition task. So feature learning means that neural networks can automatically focus on the key aspects of the data. For example, in this task, like features such as like noses, eyes, contours of the faces are the key aspects of data, and will be very useful for the task. And the hierarchical learning means that neural networks tend to learn the simple feature first. For example, the edges, which are learned by the lower layer neurons, and then progressively learn more complicated features, like the noses or the contour of the faces. These two abilities usually are thought of the reason why neural network are so successful, and we may want to ask this question, like, can classical kernel methods, which are simpler and more interpretable, also achieve these properties? So a common belief is no, because kernel methods, as you know, use fixed features, and these features cannot adapt to the data. Therefore, no feature learning will happen. Let me illustrate this difference, and this is true. And let me illustrate this using a simple example. And we will focus on a simple task. We will learn a sparse and high-dimensional polynomial function. Here, the underlying true model is a degree 3 polynomial, and the data is randomly drawn from the hypercube. So in this plot, the input dimension is pretty high, it's 100, and the y-axis is the test loss, and the x-axis is the number of samples. You can clearly see that there's a gap between the kernel machine and the neural network. So so there's a gap. There's a gap between the performance of the kernel machines and the network, which verifies our common belief. And in this talk, I'm going to show that indeed we can bring the feature learning and the hierarchical learning capabilities to kernel methods. It's an answer to this question. Okay, let's review the kernels. I believe you're pretty familiar with this method, so I'm going to go over this slide very quickly. So let's say the original data is a two-dimensional vector, and we want to separate. We want to learn a linear classifier on this classification task. On the original data space, it's impossible because the data is not linearly separable. But if we apply a feature map to the data and lift the data to dimension 3, and clearly there's a hyperplane that can separate these two classes. And the kernel function, so in practice, the dimension of the feature can be infinite, so we need to apply the kernel check to learn a linear classifier on top of these features, and we do the kernel check, which is defined. The kernel is defined as the inner product of the feature map, and for example, Gaussian kernel, which is an RBF kernel, has infinite number of features. Okay. Furthermore, we will focus on the kernel ridge regression. Let me introduce the setup. We will consider the setting where the labels y equals some underlying function f star of x plus some noise epsilon, and we aim to find a predictor to minimize the L2 loss. For n samples, we will compute the kernel ridge regression estimator. Here the k is an n by n matrix. Theory shows that kernel ridge regression to learn degree p polynomials needs at least d to the p many samples. So this is not very good because to learn this degree 3 polynomial, theory shows that we need d cubic many samples. And experimentally, we can see that this is worse than the neural network. Okay, so here's the surprise part. Here's the surprising part. Even though that kernel regression test error is high, its gradient actually point to the relevant coordinates with with much fewer samples. So here we can compute the coordinate gradient of the kernel ridge regression, which essentially is the gradient of the kernel, gradient of the square of the gradient of the predictor. Let me visualize the gradient. Here the y-axis is the number of samples. You can see that to learn this function, we need d cubic many samples. But to identify the 3 important coordinates, indeed, we only need d to the 0.6 many samples. It may not be super clear, but when the number of samples is d to the 0.8, it's pretty clear. Like there's a separation between the first 3 coordinates and the rest 2. Indeed, our theory shows that square root d samples suffice to identify the important coordinates for this function. And there's a very natural idea. We can use the identified subspace, which are the top 3 coordinates, and we project the data to this subspace and then learn the function with the project data, and then we can effectively reduce the dimension of the input. And this is the idea of our algorithm, IRKM. So the step-by-step diagram of algorithm 1 is we first fit the kernel ridge regression to the data. Here we consider a parameterized kernel. Specifically, we multiply trainable parameter w. We multiply the square root of w. We multiply the input data by the square root of w, which is trainable. And then we compute the coordinate-wise gradient magnitude. And then we normalize then update the weights based on the gradient magnitude, and then we repeat with the fresh sample because this is an online version. So you can think of this as a kernelized iteratively reweighted least square algorithm. When the kernel is a linear kernel, it's exactly IRLS. And this work is heavily inspired by the recursive feature machine. But here we specifically update the diagonal. We specifically update the coordinates of the data. And we have a safeguard parameter, and we normal data. These 2 steps are pretty important when we do the feature learning and hierarchical learning, as you will see in the next few slides. Okay, so far so good. Let's see some experimental results. As you have seen, that there's a gap between the kernel machines and the neural networks, but now we update the kernel based on the gradient, and even the 1 step of the IRKM, it already outperforms the neural network. And if we do the multiple step of IRKM with d to the 0.6 data, the test source is already like near optimal. And then we can visualize the gradient of the multi-step IRKM. We can see that with much fewer samples, it can identify all the coordinates and achieve pretty good results. Okay, let's move to the hierarchical learning. Now we consider a staircase function where there are some coordinates that only interact with high degree terms. For example, in this function, the coordinates x3 and x4 do not appear in the lower degree terms. And as you would expect, that kernel ridge regression with like roughly linear samples can only identify the lower degree term, which is actually the case. Here you can see that only the first 2 coordinates are identified by the kernel ridge regression. And the interesting thing is that IRKM can progressively learn the higher degree terms. It first picks up a coordinate x3, and then it picks up coordinate x4. So here, actually, the safeguard parameter is quite important because we want to maintain the the magnitude of each coordinate to be like appropriately large. Then it can be picked up later. Otherwise, it will just be impossible to distinguish the high order feature from the noise. Yes, and the sample complexity of learning such class of function actually is captured by the concept of leap complexity, which essentially means the number of the new coordinates introduced at each level of the hierarchy. So for this case, the leap complexity is 1, because like from the from the constant term to the degree 1 term, like there's at most 1 new coordinates, and at each level there's at most 1 coordinates introduced. Therefore, the leap complexity is 1. And here's our informal theorem. Indeed, we show that for sparse functions with leap complexity p, IRKM can learn these functions with d to the p minus half many samples. Compared to the neural network, literature shows that neural networks needs d to the maximum between p minus 1 and 1 samples to learn the leap complexity p functions. They're saying when p is less than or equal to 1, IRKM does better, but when p is greater than 1, neural networks can do better. But our empirical results show that even when the leap complexity is 2, IRKM still perform better than the neural network, and this is a deep, fully connected neural network. And we believe there is some room to improve the sample complexity for the IRKM. This is ongoing work. And lastly, we can extend the IRKM to unknown basis, which becomes the online version of RFM to learn some multi-index model. So the key difference is that we compute a weight matrix instead of a weight vector, which is essentially defined as the average gradient out product plus some safeguard term, and then we normalize the eigenvalues accordingly. And so in this experiment, the target function is a multi-index model with degree 4, and we compare the performance of the neural network with the multi-index with the RFM, and it turns out that RFM does better. Okay, let me wrap up. So I've shown that kernels can do feature learning and hierarchical learning through iterative reweighting. And IRKM is a simple, interpretable, theoretical justified algorithm. And it is competitive with neural networks in sample efficiency. Actually, in all the experiments, I have shown that it's always better than the neural network. And here's a paper link, and thank you.
So you didn't say anything about kernels, like which kernel you use.
So in all these experiments, we use Libin kernel, but we also do like Gaussian and I think NTK in the paper.
Right, but your results seem to be independent of the kernel, the RKHS.
Yes. I mean, our theory actually applies for any like inner product or like.
I see.
Yeah.